Hello, and welcome to this low-level JavaScript series, where we are attempting to build the world's first RISC-V CPU on an FPGA in TypeScript. Now, we're kind of down the road on this journey. It's now episode 7, and we still haven't done any specific FPGA stuff, so still making bold claims and not really following on them. But actually, we're doing a lot of prep work at the moment. And what we're doing, just for those of you who either have forgotten or just need to catch up, we're writing an emulator for RISC-V. And we're writing a very low-level emulator. And basically by that, I mean we're writing an emulator which is actually going to do basically all the stuff that the hardware is also going to do. And this is just allowing us to really easily iterate, debug, try programs, get kind of the design worked out, as well as exploring the architecture and the instructions and how they're encoded and how the pipeline stages are laid out and how they pass data between each other and all of that fun sort of stuff. Now, in the last episode, we actually worked on unconditional jumps. That is ways where we basically get to a certain point in the code and we want to go somewhere else. Like we want to call a function, or we just simply want to be at a different place in the code. Maybe we want to return from a function. And RISC-V actually, it implements those all with two instructions. Jumps and calling and returning and all those kind of things, all with two instructions. Super clever. I think it's really cool. But what that doesn't cover is branches. And branches are slightly different. They are the idea that we might want to go down two different paths. So depending on something, right? This is conditional stuff. So, we've got ifs, while loops, for loops, all the other possible things you can think of for basically when you need to change your position conditionally in the code. So for that, we need to implement a new opcode and a new set of instructions, which are going to be these branch instructions. So before we dive into that, let's just go over some follow-up business quickly. Now, in the previous episode, we ended up with these two signals that go through the pipeline stages. One saying if the instruction that we're currently pushing through is a jump, if it's a jump and link, or if it's a jump and link register. And it was kind of obvious by the end that really all you needed was something called isJump, and then that kind of does the job, because anywhere that we needed to basically talk about isJump, we were saying isJAL, bitwise, or isJALR. So I just went in and added that signal. And I think we are going to have to put it back today. But that's fine. Actually, it's good to have this main isJump signal move through the program and then move through the pipeline rather, and the isJAL or JAL, that one is going to probably need to perform a specific task. So we're going to probably need to get that back out. I fixed a bug that was reported by Padake. Apologies if I didn't pronounce that correctly, which was that in the A or U table in the execute stage, the operation that should be OR was also just saying if case XOR when there was already an XOR. So, it never would have worked, and I haven't actually tested that piece of code. So it wouldn't have worked. But luckily that was nicely spotted, and I've gone in and fixed that. So thank you for that, Padake. I also fixed another bug that I had introduced myself. Well, I introduced all these bugs, right? I'm the bug master in that way. So I introduced this bug, write back value valid, and I stupidly, when I was writing into this value is written in the memory access stage, and I'm still not sure if that is the best place for it, or if it should be built up as we move through the pipeline. But this value is basically telling the next stage, the write back stage, whether it should perform a write to the destination register. And I stupidly had isStore set up here. So somehow in testing that worked, because I don't really know, but luckily we just didn't write into any registers that we needed. But we were writing into a register on every time we did a store, and it was sort of like, that's not the best. Anyway, so now I switched that over to isLoad, and that actually works properly. And one thing I did just really quickly, just because I thought it would waste time, on this episode, is I added a debug kind of breakpoint interface so that we can actually break on certain program counter addresses. And it does just use the internal breakpoint system of JavaScript. It's going to just use the debugger keyword to pause the program. Basically, we can add and remove breakpoints on the RISC-V class itself just by calling add breakpoint with the address. And yeah, I think that's quite handy, just because when we're reading programs out, like in the, when we have them open in the terminal, or if we have them open next, like the disassembly, then we're going to have it's going to save, counting instructions when we're going through and trying to test things out. So that's why I did that. It's not too exciting, actually. There is a private breakpoints up here. It's a set of numbers. You can make this more sophisticated, but there's a set of numbers, and when you call add breakpoint, it simply pushes into that if there isn't already a breakpoint there, and when you call remove, it takes it out. And the only thing that happens here is when we call cycle, if the stage that we've just finished processing was the instruction fetch stage, then we look at the program counter that it just pushed through to the next stage, and we check if we have a breakpoint there, and then we break. Super simple. Could have written it on in the video, but I wrote it just now so that we have it ahead of time. And yeah, you can see how that works. I add a breakpoint here at the beginning of the program, and if I run it, yeah, we just trigger here, and that's different. We used to trigger after the instruction had finished. We had a debugger built in here, and I just removed that. And I thought, if you want to look at this like when the instruction is done, you can just you could just go and put a breakpoint in the instruction, in the write back stage at that point, and just see what the result was at the end. So this is probably going to be quite useful, because we can just add those breakpoints via the debug interface as we're analyzing programs. Anyway, that's it for follow-up. So let's actually get into it. So implementing branching. Branches are very similar to jumps, right? Fundamentally, what we're doing is we have an instruction that somehow specifies an address that we're going to jump to, and it also specifies now some kind of condition. And if the condition is met, then we should jump. And well, the thing here, right, is that I have in this thing, injected some code there. So we're actually now calculating branch addresses. So we're saying that branch address is a signal that decode produces, and then basically in the index, when we wire everything together, the instruction fetch stage, every time it runs, it's looking to see, do I actually need to take the address that maybe has been produced by a branch instruction or some branching kind of thing. So it's got these two methods it calls. It calls get branch address and get branch address valid. And so what it does is it looks at the output of the decode stage, checks to see if the branch is valid, and if it is, then it will jump to that branch. This works for jumps, but it's not going to work for branches, because branches aren't going to be able to analyze whether the condition was met until the execute stage. And so what we're going to do is we're just going to move all of that forward one stage. We're going to move the branch address and the branch valid stuff forward into the execute stage, and that way both types of instructions will inform after the decode stage. Hope that makes some sense. In pipelining terms, that is going to mean that it creates a hazard, right? Because if you don't know that you have a branch, if like you can know that you have a branch, and you can know that you have a jump instruction coming up, but you've got this one moment of delay where where you're still going to process an instruction, right? You can still push something through the pipeline, and that thing might end up being wrong, especially if it's a branch. If it's a jump, you actually know it's going to be wrong because you already know you're going to jump. But yeah, we're going to get to that later when we talk about parallelization of the pipeline, because none of that will have an effect while we don't have a parallel pipeline. So just keeping things simple now, we'll just move both of those things forward. And really all that is moving the branch address calculation forward. So instead of doing this whole thing, we would just say that we have a 32-bit immediate here, and we'll just make it probably this slice 32, right? And then in the next stage, we'll know that we have this certain kind of jump, and so we'll add that to RS1. And the other thing here is that I'm not sure. I guess it depends on how this is ends up being in hardware, like how the register file ends up being. But I'm not sure if we'll have actual access to the value of the register during the clock cycle that we're sort of pulling it out. It's possible that we will. Yeah, I can imagine a world where it's implemented in a way where you could do that. But yeah, you never know. With timing and things, that might become an issue. And so in the next cycle, in the next pipeline stage, we know for sure that value is going to be around, so we can actually do the addition and everything on it. All right, so I think that covers some of that. So branch address should be calculated in the execute stage. Conditions will also be assessed in the execute stage. And when we branch, the only real big difference between branches and jumps is that, well, aside from checking a condition, is that when we branch, we're not going to store the return address anywhere, right? It's not like a jump. We're not calling a function or something. We're going to a different place in the code with the presumption that we're not coming back to where we are. We could end up going back to where we are, but not through a return mechanism. Okay. Later on, we might talk about branch prediction and RISC-V's kind of prescribed heuristics for how that should kind of work, and how the compiler should generate code, and then kind of how you should start thinking about writing a branch predictor based on that. But branch prediction, I mean, I'm not going to touch that for now. I mean, that is something we could get into when the CPU is running, because it's something that if you add it in and it works well enough, and especially if you follow RISC-V's heuristics, right, part of the ABI in that way, then you can actually get a decent performance increase in your code, especially when we have a parallel pipeline. None of that will make a difference if we don't have a parallel pipeline. Okay, and then we're going to talk about, when we get to the execute stage, I want to break out of this big switch statement that we have. And let me just go and get this switch statement. We have this big switch statement now, and in here we calculate an ALU result, and we kind of create an addition result, we kind of create a shift result, and all of these different things. And we create a result for that, and effectively in hardware terms, we're going to do all of that at the same time. We're going to do all of that in parallel, and then we're going to kind of multiplex those signals together and choose the one we actually want to kind of exit the stage based on this funct3, right? So it's kind of modeled the way we're doing it here, but we're actually calculating only the value we need. And the thing about the branches is they're going to use some of the values that we actually have here. Like, for instance, they are going to use, they can also make use of this result, the set less than. So they can understand, for instance, you can branch if one value is less than another value. And certainly if that's the case, we kind of want to be able to use that if we're branching as well. So we're going to try and kind of get this to a place where we start modeling the parallelism a bit, and also the ability to kind of make a little bit better resource utilization of the ALU itself, so that things have multiple purposes, and we use them where we can. All right, so yeah, I mean, I think first things first, let's just take a little look at the spec. Realizing now I need my little window here for switching between scenes. Let's take a little look at the spec. So this is the handbook, but we want to look at control transfer instructions. It's still highlighting the JL instructions. Okay, there we go. I don't know why that's bothering me. It shouldn't. Okay, so when we get to conditional branches, oh yeah, the whole branch predictor thing. Yeah, we're not going to talk about that now, but this whole section here that talks about heuristics for that, and it's actually pretty interesting. Okay, so conditional branches. Branch instructions use the B-type format, right? So this is going to be the first time we use the B-type instruction format. The B-type immediate encodes a 12-bit signed offset in multiples of 2. So that's very similar to what we were doing with the jump addresses, in that you can see that this immediate, which is also kind of divided up into the instruction a bit. And there is a reason now, and I now understand the reason, I think, a bit better, although it only really applies to this, and it doesn't really apply to the jump, so I'm not sure, actually. Yeah, it doesn't quite apply here, so maybe my reasoning was off. But what I was thinking was, oh, okay, maybe it's divided up because we actually want to keep the positions of these registers in place, you know, and everything. But that sort of doesn't matter, right? Because then you could still keep that part kind of consistent instead of having that bit down here. In any case, you'll notice that this offset that we end up calculating, we end up pushing these things together in the right order, and we get an offset. And it doesn't specify 11 down to 0, it specifies 12 down to 1, and that means that there's a kind of implied 0 there. Yeah, so it's the same here as it was in the jumps. And you can see that gives us an effective conditional branching range of 4 kilobytes in either direction. So that's kind of, yeah, that's kind of an interesting thing. Like, you can't conditionally jump very far effectively. If you have a big program, that's actually not that far. So yeah, like, well, I mean, that's also kind of normal. I don't think you end up conditionally branching to huge places otherwise, but yeah, because you also can think about that being bad for your instruction cache, which we also don't have, so there's no talk about caches at the moment. Okay, so branch instructions compare two registers. Maybe I should actually turn on the light in this room because it's pretty dark, and I don't know. Maybe during the course of this recording, I'll hopefully there's no like 50 hertz thing there. Anyway, during the course of this this thing, I don't want it to get too dark, and it could happen. Okay, so we end up comparing two registers, right? RS1 and RS2. Branch equal and branch not equal. Take the branch if registers 1 and 2 are equal or unequal. BLT and BLTU, which are a branch less than, take the branch if RS1 is less than RS2 using signed or unsigned comparison. Branch greater than or equal to, branch greater than or equal to unsigned, take the branch if RS1 is greater than or equal to RS2. And yeah, and then it talks about some pseudo instructions of how you can basically use combinations of, you can basically kind of swap around operands of those 2 instructions or those 4 instructions and create all the other kinds of things you'd want to do. And also note that we only really kind of need to do like one bit of work for this, for the less than stuff, because we're checking less than. Notice that greater than or equal to is just the opposite of that. So if something is less than, the other one by definition is greater than or equal to. Wait, does that make sense? No, the other one has to be greater than. No, just forget that. But yeah, so yeah, there are some pseudo instructions as well that give us like the rest of these kind of operations that you want to do, so you can still specify them in assembly language easily, which is nice. Okay, I guess there's one little note here about the way in which things should be taken. So I'm kind of all over the place here, thinking the other one. This is about branch prediction specifically, and not the kind of other side of the coin up there. But software should be optimized such that the sequential code path is the most common path, with less frequently taken code paths placed out of line. And what that means is you should assume that most of the time your conditions won't be taken, right? So if you're checking if something, then do this thing inside. You kind of want to structure you want the assembly stream to come out so that like the most common case, either that you're doing it or that you're not doing it, like that ends up being like the thing where you don't take a jump. Because yeah, if you just think about it, it just means that the program counter keeps ticking up. And rather than like, if you say that you assume branches are taken, that means that you always need to send the new PC, the calculated one, back and all of that kind of stuff. And yeah, there's the whole instruction cache thing that we don't need to talk about now. But of course, like when you're caching instructions, like you don't, like in the best case, you don't want to go to memory for all your instructions all the time because it's slow. So you want to have like kind of little mini stash of your instructions, like, you know, close by the processor so it can get them really quickly. And you kind of want, you want that to be, you know, you want that to be full of the instructions you need all the time. And the more, you know, caches cost real estate, you know, they're not, you know, they cost resources. So you can't, you know, your caches can't be too big. And if you assume that you're taking jumps, then that means that you kind of don't know what's going on with your cache all the time. Like you might be, if you're taking jumps all the time, then your caches maybe need to be refreshed much more often, which is slow. Okay, so I said I wouldn't talk about it and I ended up talking about it. No worries. Okay, let's just take a quick look on page 104 where we see the table. And these are all branches, and you can see that just like the ALU type instructions, funct3 encodes the thing that we're doing with it, right? All right, and this is our opcode, so let's just take that first. And I've lost my little window. I need to say that should stay on top. All right, so let's go back to the code. Let's open up decode. It's always a good place to start. And I guess we're gonna say, well, let's just put that here for now. And let's say that is branch. And of course, we are branching if that's our, oh, all of these need to move around a bit. Let's do that. And we need to calculate the immediate. So that's the next thing. So that's kind of the immediate. And we're going to be doing a similar kind of operation to what we did last time. So let's just go and take a look back in the document. Go back to that control transfers page. And so just like in the other one, bit 31 represents bit 12, although in the other one didn't represent bit 12, represented bit 20. So we want bit 12, no, sorry, bit 31 of the instruction ends up being bit 12 in our representation. So that's what we're doing here. Then the next part is we need bit 11, which is at position 7. So then we get bit 7, the instruction going to bit 11. Then we're back up here. Bit 30 down to 25 is going to position 10. So 30 down to 25. So that's a slice from 30 down to 25. The instruction going to bit 10. And then finally 11 down to 8 goes to position 4. So slice 32, 11 down to 8, the instruction goes to position 4. Alright, then all of that gets shifted by 1, and then we sign extend the whole thing. And we have 13 bits here, right, this time. So 13 bits. This is the value. Whoop. Please sign extend. That's our branch immediate. Okay. So now we've calculated the immediate. Oh yeah, and we have this. I already know that we're going to need to do this thing, right? Because since we're going to calculate the branch address in the next place, you can see we need to do something different if we have a JL, right? Because branch address ends up being PC plus the immediate, or it ends up being RS1 plus the immediate. And in branch instructions, it's also always the PC that you're doing something relative to, right? So these are your comparison registers. They're not acting as a base here. So you're jumping relative to the PC. So since we're jumping relative to the PC, what we can say is if we have a jump and link, or we have a branch, then calculate the branch address this way. Otherwise, calculate the branch address like this. And we'll always calculate a branch address, whether or not we're actually dealing with a branch kind of instruction or not, right? Because we have the hardware anyway, it doesn't cost more time to do it, so we'll always calculate a branch address. And it will just be the case that we don't care what this comes out to be if it's not either a JL or a branch. Like, kind of, if it turns out to be a JLR, obviously it's going to calculate the right address, but if it's any other kind of instruction, we actually just don't care. We're not going to use the branch address. Because branch address valid will never be true, so we'll never jump to it. Hope that's clear. Okay, so we need to now re-export JAL. So let's do that. Let's actually make a first cast is JAL after having gotten rid of it. Alright, so let's move this up by 1 and let's turn it into a this.jl. Oh no, that's JLR. Should have left it as is. This dot is JL dot value. So that's still all good. Then that's this dot is JL dot next value instead. This. Ooh. Whoa, what's going on here? Next value. And for now, I'm just going to comment these out. So I'm going to forget otherwise. So this is kind of funny, right? In the previous one, I ended up, setting iMmedia to this and being like, oh, okay, it doesn't matter what that is. But actually, the immediate that we're adding is this. So let's set that. I guess I don't need to keep this around, right? It's just that this one is PC relative and this one is going to be register relative. So we calculate our correct immediate. This kind of feels wrong that this isn't in its own immediate thing, right? But this is a derivation for the immediate, so I think it's fine. Yet we get all of that, and we don't use branch immediate yet, so that's actually the next thing to do. Let's write is branch dot next value. Then the immediate becomes the be immediate. Yep. I think this is okay. Just have the feeling maybe this should be, oh, keyboard. Maybe I should do it like that instead, so that one comes on the end, but it actually doesn't matter at all. So then we need to be latching the values, because right now we're not latching JLR and we're not matching its branch. So let's do that. Is jump, is JL, is branch, and then let's move those forward as well. And then we're not going to move branch address forward because we don't have that here anymore. We're not going to do that. I don't think I've mentioned it anywhere else, but we'll see. Yeah, no. If we get rid of it, yeah. So I think we're in the clear here now. Yeah, so let's go to execute. And now let's just kind of fix things so they work properly now. So that nothing should change at least. So we need a branch address. So let's just do that here. Oh, we had branch valid as well in here, I guess, right? No, there is no branches valid thing, right? That's the whole thing. It's computed based on this other. Okay, so let's think about this. The branch base. The base address of our branch here, what we said was that it's PC relative in the JAL or the isBranch case. So decoded.isJL or decoded.isBranch. In that case, then we want the base to be the PC, and otherwise we want the base to be RS1. Okay, so that's the don't care part, right? We obviously, if it's a JLR, that's fine. If it's anything else, also fine, but we're not going to do anything with it. Let's make a register for branch address. Oh, that's nice. Yeah, it was the last thing on the keyboard, clipboard. So this.branchaddress.value is going to be the base plus the immediate. And it's nice, right? Because now we don't care like what immediate we add to this. It's always going to work. I think that's so nice. So beautiful. You might be thinking like, oh, we're using this add circuit here. Maybe we could use the add here instead, right? Since we talked about sharing resources. And we could, but in things that I've seen that talk about like reference designs, and they usually just have a second adder for this. So I'm going to do that because it's also the simplest thing. Like maybe there's a world where this makes sense to kind of integrate it another way, but maybe it just ends up like making that, we talked about a couple of episodes ago, like making that part of the digital logic, the combinational logic, making it longer, and maybe that isn't what we want to do, like adding a bunch of kind of muck stuff up front. We'll see. Anyway, so now we have the branch base, and we need to latch that. So let's latch that branch address, and then here branch address. Okay, and then in the index, like we no longer want to look at DE for this. We now want to look at execute, which means we need to label the execute type, and we're going to go into x.get execution values out. We should just call all of those get values out or something. Yeah. So that's how we get the address. And to get if it's valid, well, that's going to be a whole different thing, right? Because now, yeah, actually, I think I want to add a first class value for that, like a first class thing we send out. We'll just call it branch valid. And for now, the current way we tell if a branch is valid, which we can use just for now, and we'll extend this in a bit, is just to say like decode is jump, right? If it's a jump, then it's valid. And let's latch it. Branch valid. Okay, so then in index we will look at the, like, I just want to make this something more like this now, and we'll say this dot x dot get execution values out dot branch valid. Okay, that kind of simplifies that now, right? We know if the branch is valid and we know if it's an address, and right now it's always valid if it's a jump. And what we're going to do is we're going to add on the condition, like if it's a branch and the execution, so it's a jump or it's a branch and the execution execution, and this comparison operation that we're doing is also valid. Great, so I think we're in the same position we were before now, except of course we're now computing this one instruction stage later, pipeline stage later. All right, and now what I want to do is I want to pull these values out of the switch, and there's only a couple of them, so it's not going to take very long. So let's just do that really quickly. So let's say we get an add result, and I think because there's this, I'm not going to change the structure of the code too much, so I'm just going to do it like this. Add result, set it to 0 initially, and like cut that, and we will say that if it's a register op, then this is going to become add result, and then this whole thing actually needs to be like run through the to's function, because now we're no longer doing this with the register 32s. So add result, and then this goes through the 2's as well. That's fine. I'm all right with that. And then here, this is going to simplify to was it this dot ALU result dot value equals add result, and then we'll break from there. And then like now we're gonna make this a bit shorter as well. Okay, so that's one done. So let's get const SLL result. This one we don't need to reassign. We don't have a thing here, so we'll just do it like this. Whoop. Wrap that up in a to's function like this. This .ALU result is SLL result, and then comes up here. All right, so then we have, well, these are out here a bit. So const SLT. So this is kind of funny because we're untoosing and toosing, and but it's all good. SLT result here. And then we have the same thing, but then unsigned. SLTU twos. that should be result. Set less than unsigned result. This is like the kind of tedious work, kind of just really sort of just too annoying to automatically refactor. I mean, it's definitely doable to automatically refactor this, but I think in the end, while it's less satisfying, it will take about the same amount of time. It's like there's only 8 of these values, so. Alright, that's that. We had this const sr results. This one has a double nested ternary instead of an if statement, so probably could just do that also for the add as well, but I'm not. I could have also twosed all of these things like in this moment. Maybe that would be like, that would also be easier. Doesn't really matter. Then we get or. Or result. Blah, blah. And then and. Intense concentration for this extremely focused job. Break. Alright, so that's functionally equivalent. Now we just have a bunch of stuff that we're doing in parallel, which we actually will do in parallel on the actual hardware. Now we need to do a couple of extra checks here, so let's just do them. Let's do them in the naivest possible way, and then think about better ways later. So here, let's think about what we need to do. So we have equal, not equal, less than, greater than, less than unsigned, greater than, equal, unsigned. Let's make an enum, just like we did with the ALU operation. So what's this going to be? This is going to be branch type. No, it's not really a branch type. Yeah, branch type. Why not? Okay, so we have equal. Let's do it like this. OB, and I need to make sure here because I'm pretty sure they don't go in order. I mean, they start at 0, so 0, and then 1, 0, and then it's 1, 0, 0. So 0, then not equal ends up being 0, 0, 1. Should focus here because I made a mistake in this kind of thing last time. BLT 100. I see there's a place where I've made a mistake around. BLT 100. Then we have BGE, which is 101. Then we have, should be, yeah, less than, equal, unsigned. Sorry, less than, unsigned. So that's branch less than, unsigned. and I didn't look at the number. Branch less than unsigned is 110, and then the last one is 111. 110. So that's branch greater than or equal to 111. And I will just double check this afterwards, I think, just to make sure I'm not wrong. Guess that. Oh, okay, yeah. So these two. Yeah, cool. All right, 0, 0, 0, 1, 100, 101, 110, 111. 0, 0, 0, 0, 0, 1, 100, 101, 110, 111. Yeah, looks good, I think. Cool. So now we can actually go and make results for all of those as well, right? For the ones we need at least. So we need equal, so let's have an equal result. And that's going to be the 2's complement. We don't need to do 2's complement for these because they're going to be just 1s or 0s. So these always compare RS1 and RS2. So so what's it going to be? Decoded.rs1. RS1 is equal to decoded.rs2. And then, of course, the not equal result, well, we can just invert the equal result. And yeah, I did this differently in the last one, I think, but I'll do it like this way for now, just to show that you can do this. I'm sure everyone knows anyway, but do it like this. We can invert the bits, which will invert every bit, which is not what we want, so we can end off just the one bit that we care about at the end. Alright, then we have the less than. We don't need that because we have these two here, right? Set less than. We do have the greater than or equal to, so greater than or equal result is going to be, and we need to untwo's these things, so let's do that. Untwo's decoded RS1 greater than untwo's, oh, thanks for this code, decoded RS2, and then we want that whole thing to just, we'll cast it to a number, right? All the different possible ways you could do this. Then we have the unsigned version of that, which we don't untwo's things on. Okay, and that's it, right? Yeah, we ended up having 6 of those, right? 1, 2, 3, 4, 5, 6. Yeah, perfect. Okay, and so now we can do something like this. Maybe I'll do it above the. It doesn't really matter where we do it, but I'll do it below. Okay, so I want to know if the if this branch should take branch condition met, and in the case we'll say 0, then we can switch on decoded.funct3 just like we do for I'm not going to mix those two things together, right? There's no point in like squishing the code together for those two things. Let's just do it twice. It's not worth it for how difficult that will make me not doing bugs. Okay, so for that we want to look at branch types and equal. So if we're dealing with an equal, then our branch condition met is going to be the equal result, and then it's just the same as the AOU thing, right? What doesn't it like here? Boolean not assignable to number. Oh yeah, that should have been cast to a number as well. Yeah. Okay, and then if we have a not equal, then that's going to be the not equal result. Easy. If we have a oh, I've kind of named these weird, right? I thought I was naming these after like the instructions, right? BEQ, BEN. Oh, BNE, sorry. Okay, let's actually fix those. So I think I can just refactor this from here. So that's a neck. No, it's not neck. What am I talking about? It's beck. Yeah, of course that makes sense. All right. This becomes beck. This becomes B and E. And then let's deal with our less than. So this one is going to be the set less than result. The unsigned one, because we can just do that. Then the branch greater than or equal to is going to be our greater than or equal to result, not the unsigned one, the non-unsigned one. And then the unsigned one goes here. Okay, and then at the end of this, we can now figure out the proper value for if the branch is valid. And let's just move this down here and just put all this logic together, although it's kind of strewn apart. The branch is valid if we have a decoded jump, or if decoded.isBranch and the branch condition was met. Like, though, if any of either this condition and these two conditions are true, then the branch is valid. And that's it. I think that now covers the stuff we had to do for the index. And I want to dare to say that that might be even the only thing we need to do. I feel like I'm forgetting something crucial, but I guess we'll see. So, how to test this? I think the easiest way to test this will be to write some C code, because it's just a little bit simpler. So this is what we had last time. Let's make this as simple as possible. I also played around with adding initialized constant like read-only data that's embedded in the program. So when you generate this, this gets like created somewhere in memory, in the same place that the code gets loaded up at in the program run. So that's just nice to see. So yeah, I think like can make this pretty straightforward. Why is that now complaining? Oh, because I was messing around with the global. Yeah. Let's not generate this function anymore, because don't need it for now. And how can we do this? Let's say we have int a, which is 5, and we have int b, which is 8. And then we can have an if statement, which just says if a is less than b, which it is, then let's write to ram address, ram star, and we'll write 42 in that case. And otherwise we'll write, we'll write 1. So we would expect to meet the condition here and to write 42. And we can just come in here and flip this around and do some other stuff with it and see if we can get this to work in the way we think it should. So yeah, testing this, the way we're going to do that, I think, is, well, I'm in this system code. And one of the other things I did, by the way, and it's not really super important for now, and all this stuff could change, but I went and I wrote a make file instead of this script that I had, and the make file is not like amazing by any means, but it just makes it a little bit easier to test things out and structure the code in a bit better way. So I made this make file, and I also just added this other assembly program which has a few routines for doing multiplication and division, right? Because we don't have hardware support for those, so I put these in. And these have standard names that like if you try to do a multiply operation, the compiler will emit like a call to this function. It assumes that this is built in somewhere. So either what you do is you allow the compiler to generate things for you. So in this case, you would allow it to generate this. And then the problem is that it actually generates this plus a bunch of other stuff that I don't really want or care about at the moment. Maybe I do need it eventually, but I don't want or care about it now. So all I did was I went in and I generated the code with all the extra stuff, and I just pilfered a bunch of these implementations for multiplication and division, and I stuck them in this file, and now it just compiles in when we compile the program, so we can actually do stuff, like a times b. Obviously it's not fast because it has to go into a call and do stuff, but it works, so that's pretty cool. Anyway, long story short, we should be able to make this. Then we're going to end up with a new program. I'm going to put it open to the side here, where it's this one. Put it on this side because that's the side that will be easier for you to see. And let's go in this system code, and let's run the RISC-V obj dump. We are disassembling main.o, and I'm calling it main.o now as well. So you can see that we end up with a bit more code, right? There's more stuff going on, but we don't use most of this stuff now. We're not using any of that. That's just all of the math stuff I just showed you. The start section's the same, and now we don't even have any external functions. We just have main here. So yeah, this is the kind of code we come out with. We end up doing the stack stuff. Then we're loading a register with 5, because that is, the 5 that we see here in the C code. Then we end up storing that into a memory location. Then it's really funny code generation. It's because I have all the optimizations off, because if I didn't have optimizations off, the compiler would just get rid of all of this stuff, right? It knows that 5 is less than 8, so it's not going to even bother to generate code for the rest of it if it knows that's there. So I turned off optimization so that it emits the dumb code, but that also means that it does stuff like load into a register, store it at a memory address, then load into a different register, like that same thing we just stored, and then load into that first register. Wait, what is even going on here? Oh yeah, we do the 5, we do the 8, so we end up loading 5 into A5, storing it, then we load 8 into A5, we store it, and then we load the 2 back up into A4 and A5. So it's, could have just put something in A4 in the beginning, not a problem. Then we get to our branch greater than. Oh, I made it a greater than. It's fine in this case. So if A is greater than B, then it's going to do that. So we're going to expect it to write 1 in this case. Then we end up doing load upper immediate with our value. We load up the value we want to write to, because we put it in A4 because we no longer care about A or B. And we store it into the thing. And if we get to that point, we end up doing a loop forever, and then this is just the rest of the condition, right? This is like where we would branch to. So that's 11C, and you can see that that's 11C here. So like this is the other part. And then we do another infinite loop at the end. So that's pretty cool. That's it. Yeah. So yeah, and you can see the program gets a bit bigger, right? Even though we don't use this stuff, we can get rid of it, but it's fine. So what I'm going to do is I'm going to just initially set down a breakpoint, I guess, here, like when we get to this one, because we know the stack stuff works and all of that. So we'll put a breakpoint down, and then we'll just start walking through the program and seeing how it goes. So here we can add our initial breakpoint, and I'll put this, I guess I'll put it up here. It doesn't really matter. I mean, we can keep the C code in view so that we can take a look at what we're looking at, but it's so simple that it doesn't make a big difference now. So I'm going to run that, and we hit our breakpoint. So we are in fact at this address where we start storing stuff in registers. So we could walk through all of this and check that like storing stuff in registers works. I think what I'm going to do is I'm just going to break at this point, and then we can just take a look at the registers, assure ourselves that everything works, and I can show you how that works now. We do this.add breakpoint. This.add breakpoint, and we add a breakpoint here, and then we can just let it run again. So then we hit this breakpoint, presumably. We can check that by looking at the PC, which is now 108. So that's where we wanted to stop. So we're here. So if we look in A4, then we can do that by looking into the reg file. And as we know, A4 is actually 14, so we can add 10 and we get to the sort of effective thing. So A4, oh yeah, we should look at the value there. We've got 5, and at A5 we've got 8. So we've got our two things there, and then we're going to do a branch if greater than. So if 5 is greater than 8, which it's not, we're going to branch. So what we would expect is that we're actually just going to go to this next instruction. So if I run this, oh, I shouldn't have done that. Oh, I shouldn't have done that, of course. Now we don't have an easy way of stepping into the next thing, so I should... So smart. Okay, try that again. This time I'll take that, and I guess I'll load that into our breakpoint address. Take 2. So we should break at that point, and then I can stick a breakpoint there now. And then, so we're here, all of our registers should be good. I go to the next instruction. We can look at the program counter for that. So we're at 11C. So we were here, and we jumped to here. So apparently we did the branch. How can that be? Oh no, that's true. No, we ended up, wait, branch if greater than. So we're checking if, oh, okay, it just flipped the things around. So if, I guess in this case, like, yeah, because it checked that B was greater than A, and then we end up jumping. So that's funny, because that's especially not the way RISC-V says how to do it, right? But we're doing the dumb code generation. So this actually makes sense. We end up loading up this thing, and then we're going to write 1. So this was true. A is not greater than B, so that didn't work. So I'm just going to flip the sign, regenerate the binary, and come back in the code. I guess we should also do this again. Now we can see that these flip around. So all it does is flip the two things around. So now if A4, which was 5, is greater than 8, then you can see that where it jumps to will write the 1. So it kind of just rearranges the code and stuff. Apparently it prefers to do a greater than kind of instruction than a less than, or greater than or equal to, I guess, in this case. Yeah, which is the inverse of the less than. I don't know why I got so confused about that earlier. Okay, so, oh no, this isn't even going to be stopping the right address. So we get here, then we can dump our breakpoint in, go to the next address, look at the program counter, we're at 10C, so that's here. So we didn't take the branch this time, and we're going to write 42, because A is indeed less than that. So that's great. The branches seem to be working correctly. I guess we could also take a look at something like a for loop now, or a while loop. Yeah, let's just do something like a while loop, because it is a bit simpler. So we'll just do like while A. We could just do while A, and it's going to do the same thing. So we'll just do A minus minus. And I haven't tried this, so this I assume this will generate reasonable code. Make, let's take a look at what we got from that. Shorter program. So what we get is, yeah, so we end up coming in here. We put our 10 into A5, we store it at an address. Then we jump down to like where we do the condition check. So we jump down here to, oh, this is funny. We jump down to just before where we actually load the value out of memory. And then we do the branch stuff. So let's take a look. We will put our, I guess we can put our, we need a more effective way of peering into the state of the machine. Like maybe turn on like some debug mode where it can actually just spit the contents of the registers and all things that we care about out, but this will work fine. So let's actually just jump into the beginning of the program. Should be fine. I don't expect that anything is not going to work at this point. Oh no, I got it wrong. Copy. Okay. So run the debugger. Wait till we hit a breakpoint. So now we're here. So we're just doing stack stuff. So I'm going to just put the actual breakpoints here. So doing the add. Then we are doing the store, then another add, and now we're actually at the point where we're loading something up. So if we execute this, and this is the beginning of the instruction, of course, so we haven't actually executed this. Now we're just at this instruction. So let's take a look at the PC, F4. Oh no, apparently we executed the instruction. Apparently I'm wrong about that. So we're here. That also means that we can check the reg file, and looking at A5 we see that 10 gets loaded. Then we immediately do a jump. Oh no, so we're storing first, so that's what we're doing right now. We're at F4 and we're doing a store, so we're storing into like our frame pointer minus 20, doesn't matter, someplace in memory on the stack. Now we are at this jump. So we're going to jump down here to 108. So let's do that. Let's take a look at the PC. So we're here, 108. So that puts us here. Now we're loading up that value into A5. So let's just do that. Let's check A5 still contains the value we expect it to. It does. So that's good. And now we're going to do a branch if not equal to 0. So as long as this isn't equal to 0, we're basically jumping back up. And yeah, this is quite, there's something in the RISC-V manual about this as well, which I think is just useful to mention now. But when you are writing a branch predictor, and when you are kind of, like when you are taking into the idea of like whether you should go down one branch or the other, whenever you have an address, which is where you're jumping backwards, like potentially jumping backwards, you know you're in a kind of loop, right? You know that like that is the structure of a loop for the most part. So that is a heuristic to tell the CPU that probably you're going to take this branch most of the time, right? Because if you're in a loop, you take the branch every single time until you need to exit the loop. So then you don't take the branch anymore. So that's a place where you want to optimize for that, right? So yeah, so it just ends up being a heuristic that you can build in. Okay, did we run that instruction? I don't think we did. So let's run the branch. We shouldn't be equal to 0, so we should jump back up to FC. Let's take a look. We're at FC. So then we are actually in the first part of the body of the loop, and that is here. It's funny because we just keep we've loaded this so many times now. So we load A5 again into we load that value into A5. Then we add -1. So we should see that A5 has gone to 9. Great. Then we should store it back and then immediately load it back again. Store, load. So we've gone through a store load cycle now, still 9, so that's good. Then we're doing another branch. And what I think we can do is just like take this address of our branch. And at this point, just add a breakpoint, put it in there, and then let's run till we hit a breakpoint, hit the breakpoint, because that was the next instruction, right? So this is still, oh my gosh. All right, so this is still 9 at this point. Then we're gonna run it, we're gonna hit the breakpoint again. This time we're at 8, 7, 6, 5, 4, 3, 2. Let's just check we are at 2, 1, and then we're at 1, and then we're going to be at 0. And so at this time, we expect that we don't actually take the branch. So then go here, and then let's just see what the PC is. And here we're our infinite loop. So that's great. I'm really happy with that. We have branches, which is a really great thing. I mean, now this CPU, this emulator, it can actually do real work, right? It can load and store. It can do unconditional jumps, and it can do conditional jumps, and it can do a whole bunch of arithmetic and logic. And that is a computer, right? You've already got computer right there. So there are a few more things we still need to do. And let's do this nice kind of ticking off of all the things we have. So we have load upper immediate. Still need to write add immediate to program counter, but I'm kind of happier now with the structure of the ALU and the execute stage as a whole, because we've pulled all this stuff apart and we've kind of put the things in there that should be there. So add upper immediate to program counter is something that should also go into the ALU. And I think for now I'm just going to do it in a stupid way and just put it like as a third adder in there. I don't know whether it's wise. It might actually make sense to have this one share the adder of the like the main ALU adder. I'm not sure. I might go and look at some other people's designs and see how they do it. But yeah, so we've got all of the we've got everything now until here. Yeah, so we've got all of this stuff now. Minus the add immediate to upper immediate to program counter. We've got all of this. And like I say, these two will become no ops. So in the next episode, let's just do that straight off the bat. If we see this if we see this opcode, we'll just do a no op, basically. Then we end up with kind of what is quite a complicated part, and we'll probably implement this stuff over the course of a couple of episodes. And what we basically have left here is the CSR stuff, which is control and status register. But kind of the implication there is with all the control and status is that we have a certain number of registers that we have to build into RISC-V that kind of control the status of the machine, and we're building a bare metal machine, and we don't have these higher levels of privilege, or these like not higher levels of privilege, but kind of extended levels of privilege, right? There'd actually be lower levels of privilege, but we don't have those, and because we don't have those, like kind of a lot of the things that you would want to do with the CPU, like the really complex stuff, like implementing virtualization or implementing like user level separation from something like kernel code, so you can run like the Linux kernel, for instance, on the CPU. Those things we're not going to have, especially not in the beginning. Like it's definitely out of scope for me now. So we have those things. So our set of CSRs, they're going to be relatively simple, but they relate to things like timers. RISC-V says that we have to implement a couple of timers, or at least one timer, but then interrupts. And then kind of the interrupt system is pretty interesting, and I think it's something we need to build into the emulator first to get a good feel for. So that's what's coming up. I want to thank you very much for sticking around, for checking out this series, and for engaging and asking questions and giving corrections and all of that kind of stuff. Thank you very much. I also want to say a massive shout out to the patrons. So thank you very much if you're a patron of this channel. It's really awesome. It's really cool that you support this channel in the way that you do. Further than that, thank you for watching, and I'll see you next time.